All right, welcome in everyone. If you've ever felt totally overwhelmed by chemistry, just looking at a page of equations and your brain goes numb, well, you are in exactly the right place. Today, we're not just doing some boring standard review. No, we're doing an absolute gunshot crash course. We're going to crack the code of this entire chapter on chemical reactions and equations together. It's going to be direct, targeted, and honestly, highly effective.
But hey, before we even think about jumping into the formulas, we really need to anchor our mindset. Take a look at this quote right here. It translates so beautifully to, "What is in your dreams today will be a reality tomorrow." I want you to literally internalize that "I will win" mentality right out of the gate. We are manifesting those goals today before we even learn the rules of the game. So let's get to work. Okay, so here's our quick roadmap. We're going to cover the basics of chemical reactions, the art of balancing, combination and decomposition, displacement and the reactivity series, double displacement, and finally, wrap it up with heat dynamics. Let's dive right in.
All right, part one, basics of chemical reactions.
So at its core, a chemical reaction is really just a process where a completely new chemical is born. You've got your original ingredients, we call those reactants, sitting on the left side, and they transform into brand new products on the right. Now, when you look at these equations, you're always going to see these tiny little letters in brackets. It's basically the secret code of chemistry. Most of them are pretty obvious, right? Like S for solid or G for gas. But you really want to pay special attention to AQ. That means aqueous, or totally dissolved in water. Oh, and PPT, or sometimes it's just a downward pointing arrow, that stands for precipitate. That just means it's an insoluble solid that falls out of the liquid and settles right at the bottom of your beaker. Moving right along to section 2, the art of balancing. Now, you might be wondering, why do we even bother balancing these equations? Well, it all comes down to the law of conservation of mass. Basically, we can't magically create or destroy matter. The total mass of your reactants absolutely has to perfectly equal the mass of your products. So let's skip those incredibly frustrating hit and trial guessing games. I'm going to give you the foolproof cheat code. It's 4 simple steps, and you always do them in this exact order. First, balance your metals. Second, balance your nonmetals. Third is oxygen, and fourth is hydrogen. But listen closely, here is the golden, unbreakable rule. If adjusting any step breaks a balance you already fixed earlier, you gotta immediately drop what you're doing and start completely over from step 1. Let's actually apply this cheat code to an unbalanced equation of iron and water. Okay, step 1, metals. We've got 3 irons on the right, so we just match that with a 3 on the left. Boom. Step 2, nonmetals. Well, we don't have any here besides oxygen and hydrogen, so we skip that. Step 3, oxygen. We need 4 on the left to match the 4 on the right, so we just place a 4 right in front of the water. And step 4, hydrogen. That 4 we just added gives us 8 hydrogens on the left, so we balance that out with a 4 in front of the H2 on the right. Do a quick double check, and there it is. Perfectly balanced. Super simple, right? All right, on to section 3, combination and decomposition. This is where the chemical drama really starts to pick up. In combination reactions, it's pretty much what it sounds like. 2 or more separate reactants marry together into one single product. For instance, if you take a magnesium ribbon and set it on fire, it reacts with oxygen to form just one single product, a white magnesium oxide powder. But hey, definitely notice that first bullet point there. You always have to rub the ribbon with sandpaper first. Why? Because you have to remove this stubborn protective oxide layer that just naturally forms on it. But once it actually ignites, wow, it burns with this absolutely dazzling, blindingly bright white flame and releases a massive amount of heat. And here's another super famous combination reaction. Quicklime, that's calcium oxide, mixed with water. Now, this reaction is so intensely exothermic, like literally if you dump the water in too fast, your glass beaker can actually shatter from the sudden spike in heat. It forms slaked lime. And what's really amazing about this is that when you paint walls with this slaked lime, over the next few days, it slowly absorbs carbon dioxide right out of the air, and it creates these incredibly shiny, beautiful whitewashed walls. Okay, now let's completely flip the script to decomposition. This is where we break one compound apart into multiple pieces. Think of it like trying to step in and break up a fight. It requires serious energy. Let's look at the thermal breakdown of ferrous sulfate. This is actually a really fascinating color timeline. It starts out as these beautiful hydrated green crystals. You heat it up, the water evaporates, and it turns into this dry white powder. But then you heat it even more, and it finally breaks all the way down into a reddish-brown ferrous oxide. But chemistry isn't just a visual thing. It's highly sensory.
When that ferrous sulfate breaks down, it releases sulfur dioxide and sulfur trioxide gases. And I'm going to challenge you right now to remember the specific smell of this. It is incredibly pungent and suffocating. It smells exactly like lighting a matchstick. Now, on the flip side, if you were heating lead nitrate instead, your memory cue would be auditory. You'd actually hear this very distinct cracking sound right inside the test tube. Of course, heat isn't the only way. We can also break things apart using electricity, like with water. This is called electrolytic decomposition. And here is a classic memory trick you should absolutely steal. PAV, positive anode oxygen. At the positive anode, you get oxygen gas, which is known for rekindling a glowing flame. At the negative cathode, you actually get double the volume of hydrogen gas, and that one burns with a very sharp pop sound. Oh, and a quick pro tip for you, pure water actually doesn't conduct electricity very well, so we always have to add a few drops of acid just to kickstart the whole reaction. All right, let me throw a quick question out to you guys. In chemical laboratories all over the world, silver chloride is strictly stored in these thick, dark, black bottles. Why do you think that is? I mean, what exactly are we trying to protect it from? Well, if you guessed light, you hit the nail on the head. This brings us to photochemical decomposition. Literally, just the ambient light energy from the sun or even a bright room is enough to break down this compound. If light hits that white silver chloride, it immediately starts breaking apart into gray silver and chlorine gas. And fun fact, this exact light-sensitive reaction is the magical foundation behind classic black and white photography. How cool is that? Moving on to Section 4, displacement and a reactivity series. So, displacement is basically the law of the chemical jungle. It's when a stronger, more reactive element confidently marches in and completely kicks a weaker element right out of its compound. But how do you actually know who's stronger? Well, you use the reactivity series, top to bottom, strongest to weakest. Now, students use all sorts of memory tricks to remember this order effortlessly. One really popular trick starts with Kudu-Nalkar, which aligns the first letters to potassium, sodium, calcium, and so on. Honestly, just find a mnemonic that works for your brain, because knowing exactly who sits at the top of this list is absolutely your ultimate advantage in chemistry. Now, what's really interesting about this slide is the visual evidence of this whole power struggle. Imagine dropping an iron nail into a vibrant blue copper sulfate solution. Because iron is higher up on the reactivity series, it's way stronger. So it simply kicks out that weak copper. If you watch it, slowly the blue solution turns to this pale green as it transforms into iron sulfate. And that pure displaced copper, it gets shoved out and ends up coating the nail in this rusty reddish-brown layer. All right, almost there. Section 5, double displacement reactions. So if single displacement is a hostile takeover, double displacement is more like a coordinated partner swap between positive and negative ions. You've got two compounds, and they simply exchange partners to form two completely new compounds. And a lot of the time, these partner swaps result in what we call precipitation reactions. That means when these specific liquids mix, they suddenly form a new solid salt that is completely insoluble in water, a precipitate that literally just sinks straight to the bottom. Look at the contrast we have here. When you form barium sulfate, it drops out as this stark white precipitate. But if your swap results in lead iodide, it creates this striking heavy yellow precipitate. It's just instant, undeniable visual proof that the reaction happened. And finally, Section 6, heat dynamics, exothermic and endothermic. Here's the thing. Every single reaction we've covered today in this explainer has a strict relationship with thermodynamic energy. Basically, they either give energy away or they steal it. Exothermic reactions release heat out into the world. So when you burn natural gas on your stove, that's exothermic. Actually, even the cellular respiration happening inside your own body right now, turning the food you ate into energy, that releases heat too, so it's exothermic. On the flip side, we have endothermic reactions. These actually absorb heat from their surroundings. Remember a few minutes ago how we said breaking things apart takes energy? Well, that is exactly why virtually all decomposition reactions are entirely endothermic. And honestly, just like that, you now hold the cheat codes to the chemical universe. You know the exact visual details of some of the most complex reactions, and you totally understand the rules of displacement and thermodynamics. So I want you to claim that I will win mentality we anchored at the very beginning of this explainer. But before we wrap up, I'm going to leave you with this one thought. If breaking bonds takes energy and forming new ones releases it, what do you think happens when a reaction does both of those things at the exact same time? Stay curious, keep winning, and I'll see you in the next explainer.